This presentation will be about random functions in Excel. To get a random number from Excel, you can enter into a cell the formula equal rand, R-A-N-D, open close parenthesis, and then it will give you a number between 0 and 1, and then in this case I've copied it down and gotten myself 500 different random numbers. You have the open and close parentheses, though there's nothing in it, because open and close parentheses indicate that there's a function. This is a random function, but no arguments are needed. There's no information needed to generate a random number. The Excel already knows how to do it and what you mean. It's the nature of random numbers that, if you do this and I do this, we will get different numbers. And one of the features that people find sort of unusual and maybe even annoying when they're dealing with random numbers is that as they work on the sheet, those numbers keep changing. Excel has a concept of volatile and non-volatile functions. A volatile function will update when any sort of work is done on the sheet. It will be reevaluated. And even if the sort of data that goes into the making of that function hasn't changed, or in the case of the random number, when there are no arguments whatsoever, it will change. I'm going to let Excel be Excel and just let it just keep changing those random numbers. But one trick that people will use if they find this problematic is they will generate the random numbers, then they will copy them and paste them, and when they're pasting they will paste special and you choose values, and then those values will be fixed. It'll no longer be the formula random, which will update, but just the value of the random number that one got originally. Okay, so we have a distribution of random numbers. I have 500 numbers from random, so I have this distribution of numbers, and then we'll perform our normal sort of statistical analysis on this distribution. So we're getting the mean, the standard deviation, the median, the first quartile, third quartile, skewness, kurtosis, just all those usual statistical measures of a distribution. Each time I get one, all the previous ones are going to change because of the nature of random number function being volatile. The rand function gave a number between 0 and 1, but then I can sort of manipulate or interpret this in various ways. So in this example, I'm using an if, and I'm saying that if the random number was less than a half, I'm going to call it tails, and otherwise I'm going to call it heads. So I can use the random number function to simulate the tossing of a coin. I could use Excel's Countif function to see how many heads there were and how many tails there were in this simulation. I expect it to be half-half, but not exactly. And the Countif function has two arguments. The first is the range of data, so that was C2:C501, and I have the dollar signs in there because I'm going to use it for both the heads and the tails, and I don't want the distribution to change when I copy the formula down. And the second argument of the Countif function is a condition. Again, it's Countif, and if is looking for a condition, so the second is a condition, and this is a condition in this case of implied equality. So I'm looking for the word tails, which I have in D2, to also be equal to the word tails that I find over in column C, and then the same for heads. So previously we simulated the toss of a coin getting heads and tails. So now we want to simulate the rolling of a die to get 1, 2, 3, 4, 5, or 6. We could work with the original rand function and simulate the result of the roll of a die. But because this getting a random number, what we call an integer, a counting number, without any sort of fractional parts, because that's a common situation. Excel has a built-in function to do it, and that's easier to do it than to work from scratch with random, so that's what we'll do. So the function here is randbetween, and then randbetween takes two arguments, and the first argument is where the random numbers will that you're pulling from will start, and the second argument will be where they'll end. And this is what we call inclusive, meaning that you can get a 1 and you can get a 6. So equal randbetween open parenthesis 1 comma 6 close parenthesis and enter the function. That is going to randomly pick a number between 1 and 6, and then it was copied down 500 times. So we're sort of rolling a die 500 times. Next we have entered the possible values for rolling a die, 1, 2, 3, 4, 5, 6, and then we have used a frequency formula to find out how many times each one of those values arose in the simulation. And that's an array formula, so we highlighted 6 spots for the frequencies to appear in, and then we entered the array formula equal frequency, open parenthesis, the range of values was the G2 colon G501. That's the first argument. And the second argument was previously what we called bin values, and the possible values that can arise. And so that is the H2 colon H7. And then as an array formula, we hit Ctrl-Shift-Enter to put the formula in. The curly brackets you can see in the formula bar were not typed, but were put in by Excel to indicate that it is an array formula. And we see then it's sort of uniformly distributed, more or less, that there are roughly in the same ballpark, the same number of 1s as 2s as 3s. We could also use Countif here, like we did for heads and tails. That's another approach to get these counts. And that's nice when there is, because these are nice crisp numbers, 1, 2, 3, 4, 5, 6, then using the sort of implied equality that is in Countif sort of works. When you're working with numbers with fractions, that's a little more sort of dangerous. Computers are funny about testing the equality of fractional numbers. They're a bit better at comparing integers. Now here we've made a histogram of the results, but be careful, this histogram was not made by going to insert chart statistical histogram. Instead it was using the frequencies, so we have already done the counting, so we don't ask Excel to make a histogram because then it wants to do the counting. Instead, we've done the counting, so we're just making a column graph that we know to be a histogram. Recall that we can format axes and so on. So here we are formatting the y-axis and choosing a minimum value, whereas previously the minimum defaulted to 0. So the previous example sort of was more emphasizing the uniformity that 1 and 2 and 3 were more or less rolled the same amount of times. And changing the minimum like this may allow us to see better or emphasize the differences. Here I've gone back and highlighted the die simulation data and used the sort of more automatic histogram under statistics charts. And what I found there is I almost had to trick Excel into making a decent histogram. Remember what we're expecting, sort of six columns of more or less equal height, and it was doing on its own. It might have an empty column and then another column which was twice as tall, and just being generally difficult. So I really had to sort of finesse it and trick it, and you can see my bin width of 0.99 is my sort of best trick to sort of get it to behave and give me 6 more or less equal columns.